I mentioned lattice energy in the bonding review video. I said that lattice energy is used to predict the stability of an ionic compound. By definition, lattice energy can be defined in two equally valid ways. You can look at lattice energy as the energy required to completely separate 1 mole of solid ionic compound into its gaseous ions. You have to put energy in to separate the solid, so this would be a positive delta H value. Or you can define lattice energy as the energy released when gaseous ions stick together and form the ionic solid. Released energy means a negative delta H. You can use Coulomb's law to do a qualitative comparison between two ionic compounds' lattice energies. Coulomb's law says that the energy associated with the attraction of two charged objects is equal to a constant K times the magnitude of each charge divided by the distance between the charge centers. In the equation, Q represents the magnitude of charge of each object, and D represents the distance between the charged objects. Consider the relationships shown by this equation. If you increase the magnitude of charge on the ions, what effect would that have on the lattice energy value? Since the quantity of charge is in the numerator, you will increase the lattice energy. What if you look at ions with greater ionic radii? Since the distance between the charges is in the denominator, an increased radius will decrease the lattice energy. Coulomb's law is used to qualitatively compare ionic compounds. For example, which has the greatest lattice energy, lithium fluoride or cesium fluoride? What's the difference between these compounds? Both anions are -1 fluorides. When we compare the cations, lithium and cesium, they're both +1 ions, but there's definitely a difference in their ionic radii. Cesium is much larger than lithium. The greater the ionic radius, the lower the lattice energy. So lithium fluoride has a greater lattice energy than cesium fluoride. Compare barium chloride to barium oxide. The cation is identical in both compounds. In the first compound, the anion has a -1 charge. In the second compound, the anion has a -2 charge. You're looking at the magnitude of charge on each individual ion. We don't look at it as two chlorides with a total of -2. We're looking at each single ion in each example. So a -2 on oxygen is more charge than a -1 on a chloride. Magnitude of charge of the ions is directly related to the lattice energy. Since oxygen carries more charge than chlorine, barium oxide has a greater lattice energy. What about lithium oxide versus sodium sulfide? Both cations are +1s. Both anions are -2s. So let's look at the size of the ions. Lithium is smaller than sodium. Oxygen is smaller than sulfur. Ions with smaller radii will result in higher lattice energy. Lithium oxide, then, is the answer. There's also a quantitative use for lattice energy in the Born-Haber cycle. The Born-Haber cycle is an application of Hess's law. Remember from our thermochemistry unit, Hess's law says that if a reaction can be expressed as the sum of two or more individual reactions, then the change in heat for the overall reaction is equal to the sum of the heat changes for those individual reactions. If you can add individual reactions to write the overall reaction, you can add their delta H values. We're going to do the same thing here. In the Born-Haber cycle, we start with atoms in their standard states and put them together into a stable compound. We look at that happening in two different ways. Let's look at each change shown in this diagram. We start with atoms in their standard states. Nearly all metals are solids. Many nonmetals are diatomic gases. We want to make those gaseous single atoms. For the metal, we need to change it from a solid to a gas. What's that change called? That's sublimation. For the gas, we need to break apart the diatomic molecule. What's the name of the energy value associated with breaking a bond? That would be bond dissociation energy. Once we have gaseous atoms, we want to make them ions. What's the term for an element losing an electron? That's ionization energy that we've just been studying. What about a nonmetal gaining an electron? That would be electron affinity. Then we take the gaseous ions and bind them together. That's lattice energy. Down at the bottom of this diagram, we see a direct line from atoms in their standard states to the compound. Again from the thermochemistry unit. What do we call the formation of 1 mole of a compound from its elements in their standard states? That's the heat of formation reaction. That's a known value for lots of compounds, a value you can look up in a textbook. All these other individual reactions add together to result in the same change, atoms in their standard states becoming a compound. All these other individual values add together to equal the heat of formation for the compound. You can use the Born-Haber cycle to calculate any one of these values, so long as you know all the others. Make sure that you see the difference between the heat of formation reaction and the lattice energy reaction. Heat of formation starts with the elements in their standard states. Lattice energy starts with gaseous ions. The Born-Haber cycle says that the sum of all these individual reactions adds up to the heat of formation for that compound. Here's what a Born-Haber cycle question looks like. Calculate the lattice energy for NaCl from the following data. Of these reactions and values given, which of these is the heat of formation for NaCl? The last one. So all these other numbers plus the unknown lattice energy should add up to negative 411 kilojoules. Which of these represents the sublimation reaction? The first one, sodium changing from a solid to a gas. Which reaction represents the bond energy? The third one, Cl2, being broken up into chlorine atoms. Notice something important here. We need to make these individual reactions and the lattice energy reaction add up to the heat of formation reaction shown last. How many chlorines are there in sodium chloride? Only one. How many chlorines are shown in this bond energy reaction? 2. When we put this delta H value into the calculation, we need it to represent the energy associated with one chlorine. So we need to put in half of 242 kilojoules. Which reaction correlates with ionization energy? The second one, sodium atoms becoming sodium ions. And electron affinity is the fourth reaction, showing a chlorine atom becoming a chloride ion. Lattice energy, the last thing, is our unknown. Solve for X. You get a lattice energy of negative 775 kilojoules. That's the amount of energy released when 1 mole of solid sodium chloride is formed from the ions in their gaseous states.